Hello everyone, welcome to this lecture. So, in this lecture we will continue with our toy MPC protocol for securely computing the sum, and we will perform the security analysis, right. So, just to summarize, this was the sum this was the toy protocol for computing the sum function. Party 1 computes an OTP encryption of its bit, and then each party just keeps on adding its own bit in the received ciphertext and further release it. And finally, by the time the ciphertext the updated ciphertext comes back to P 1, it will be an OTP encryption of the sum of all the input bits, which P 1 can decrypt by unmasking the pad and announce the result to everyone. And now we want to analyze that the probability distribution of VUI is independent with respect to the inputs of the other parties. So, let us try to demonstrate that, and for that I will take a concrete execution of the protocol where all the computations, suppose they are performed over Z5. And now the private inputs in this particular execution for the respective parties are 1 0 1 0. That means, everyone will learn finally that the sum is 2. Okay. That means, everyone will know that means every party whose input is 0, from its viewpoint there are 2 parties who have participated with input bit 1. We should show here that from the viewpoint of the party whose input is 0, it could be any 2 parties who have participated with input 1. Whereas, for a party whose input is 1, from its viewpoint it is the case that there is only one other party who has participated with the input 1. We will show here that the messages which are actually exchanged in the protocol does not help him to point out which is the other party who has participated with the input 1. Okay. So, let us see the run of the protocol here. So, imagine that the pad which is used by the first party, which is picked randomly, is the element 4. Okay. I stress here it is only P 1 who knows the value of the pad, it is randomly picked. Everyone will know that a pad could be either 0 or 1 or 2 or 3 or 4, that is all. What exactly is the value of the pad, that is known only to the party number 1. So, the OTP encryption here will be the sum 4 plus 1, which is 5, and remember all the computations are performed modulo 5. So, 5 modulo 5 will turn out to be 0. Now, that will be the value of C 1 here. Party 2 will add its bit to this ciphertext. So, 0 plus 0 modulo 5 will be 0. Party 3 will add its bit to the received ciphertext. 0 plus 1 modulo 5 will be 1, which it will communicate to the fourth party, and the fourth party it will add its input 0 to the ciphertext 1, which will give 1, which it will communicate back to the first party. And now the first party has to subtract the pad. So, it will be computing 1 minus 4, 1 minus 4 will be minus 3, but minus 3 modulo 5 will be 2, and that is a sum which will be publicly announced. Okay. That means, the correctness is guaranteed here definitely, and correctness is very easy to argue here, right, because the final ciphertext C 4 which is received by the first party is going to be the summation of k plus B 1 plus B 2 plus B 3 plus B 4, and it is computing C 4 minus k modulo 5. So, C 4 minus k modulo 5 will be this entire value minus k. So, this entire value minus k, k and k cancels out, we will get B 1 plus B 3 B 2 plus B 3 plus B 4 modulo 5, and since the summation of B 1 and B 2 B 3 B 4 is upper bounded by 4 mod, the effect of mod will not happen. So, the correctness will not be violated. So, correctness is very easy to guarantee here, right. So, now let us see whether the view of every party is distributed with equal probability with respect to every candidate input values of the parties which sum up to 2. So, let us assume that say P2 is corrupt. P2 has executed this protocol, now it has gone back to its workplace or home, it has now unbounded resources, it knows the protocol description, it has learned the final sum, it has received the ciphertext 0 and it has communicated the ciphertext 0, and now it is trying to analyze and try to learn something about the inputs of the remaining parties. If our protocol is secure, then even if it is analyzing, even if it analyze with whatever resource it should not learn anything beyond what it can learn from its input being 0 and the sum being 2. Okay. So, from the viewpoint of this corrupt P2, what are the things which are not known? The value of the one time pad which is picked by the first party is not known. What was the input of the first party, that is not known. It has received the ciphertext 0, that is a part of its view, that is part of its view. So, that is there, and it has communicated ciphertext 0 to the next party, that is also part of its view. But rest of the things which are in question mark are kind of unknown for this corrupt P2. So, now based on B2 equal to 0 and S equal to 2, this P2 can think of many possibilities. It can think in its mind that it could be the case that P1 and P3 participated with 1, that is one possibility, right, because in that case the sum will be 2, or it could be the case that P1, P4 participated with 1, or it could be the case that 2 and sorry not 2 and 3, 3 and 4 participated with 1. These are the 3 possibilities from the viewpoint of P2. Now, we have to show here that each of these 3 possibilities could actually be the case for this corrupt P2, and it could be the case that indeed P1, P3 has participated with input 1, and in that execution P2 has received a ciphertext 0 from P1 and communicated ciphertext 0 to P3. We have to show that, as well as we have to show, we will show that it could also be the case that the first party and the fourth party had participated in input 1, and in the execution this P2 has received the ciphertext 0 from P1. That is also we will show, and we will also show that it is also equiprobably the case that P3, P4 has participated with input 1, and this P2 has received the ciphertext 0 from P1 and communicated ciphertext 0 to the next party. That means, we will show that all these 3 possibilities are equiprobable from the viewpoint of P2, even if it is given unbounded resources, and hence it cannot make out whether it has actually participated in this execution or this execution or this execution, which will end up showing that view 2 is kind of distributed with equal probability. It has equal probability of occurrence for this configuration as well as this configuration as well as this configuration, and hence view 2 is kind of completely useless from the viewpoint of a corrupt P2. That is what we are going to argue here. Okay. So, let us take the first possibility from the viewpoint of this corrupt P2, and remember this analysis P2 is now doing after the protocol execution. It is not supposed to analyze these messages and learn anything about the other party's input, but suppose it is semi honest. After the protocol execution, it is trying to analyze the messages that it has received during the protocol execution and trying to learn about the inputs of the other parties. So, suppose P2 tries to check whether it has participated in this configuration. It is making just assumptions regarding what could have been the input of P1, what could be the candidate one time pad that he has used, and can he would have, is it possible that he has, with respect to that input and that value of one time pad, he has sent me the ciphertext 0 and so on. That is what it is trying to analyze. So, it is making the assumption here that P1 has participated with input 1, and P3 has participated with input 1, B3 equal to 1. Now, it is quite possible that P1 has participated with input 1 and communicated the ciphertext 0 to this P2 if the one time pad which P1 has generated has the value 4. It is quite possible, and in that case once the ciphertext 0 is communicated to this third party, it could have added its input 1 to this ciphertext and forwarded 1 to the fourth party. The fourth party would have added the input 0, communicated the ciphertext 1 to the first party, and now the first party would have computed 1 minus 4, which is 3. So, this is quite possible, this execution is quite possible. A corrupt P2 cannot rule down this possibility, whereas it is now trying to make an hypothesis that is it the case that it is this second execution where it has participated. That means, it is now making the assumption in its mind that can it be the case that the first party and the last party they have participated with input 1 and ciphertext 1 equal to 0 was communicated to the second party. Well, that is quite possible again if the one time pad which was chosen by P1 was 4, and then you can see if these set of messages would have been communicated, indeed P1 would have declared the result to be 2. I stress here the ciphertext 0 which P2 has received, that is fixed here, and which has, and the ciphertext 0 which it has communicated, that is fixed, because that is what it had actually received by participating in the protocol. All these assumptions are mental exercises which P2 is making in her mind, trying to find out whether it has participated as per this first box or as per the second box or as per the potential third box, where the inputs of the second and third and fourth party could be 1. Well, that is quite possible that input of party 1 was 0 and it has picked the one time pad to be 0, in which case it would have communicated the ciphertext 0 to the second party, and now you can see the remaining messages turned out to be, if the remaining messages turned out to be like this, indeed P1 would have announced the result s equal to 2. That means what we have shown here is the following: view 2 consists of the following, view 2 consists of B2 equal to 0, because that is actually the input of the second party, and the ciphertext 1 equal to 0 and ciphertext 2 equal to 0, right. So, this is one of the possible values of view 2. What we have shown here, and of course, sum is equal to 2, the final sum, that is the overall view of the second party. What we have shown here is that this view 2 is consistent. By consistent I mean it could occur for the case where B1 is equal to 1 and B3 equal to 1, because that is one possibility which is consistent with s equal to 2, because if s equal to 2 and if B2 equal to 0, one of the possibility could be that B1 is equal to 1 and B3 is equal to 1. So, that is quite possible, and we have also shown that the same view 2 it could be also could also occur for the case where B1 equal to 1 and B4 equal to 1 and B2 equal to 0 and B3 equal to 1, or the same view 2 could occur for the case where B1 equal to 0, B2 equal to 0, B3 equal to 1 and B4 equal to 1. That means, for all candidate B1, B2, B3, B4 such that B2 is fixed to be 0, because that is actually the input of the corrupt P2, and such that the sum of these candidate B1, B2, B3, B4 is 2, this value of B2 could occur with equal probability. it could occur for this case as well as this case as well as this case. So, a corrupt P2 cannot narrow down whether it has actually participated in the execution where B1 was 1 and B3 was 1, or it cannot pinpoint whether it has participated in the execution where B1 was 1 and B4 was 1, or it could not pinpoint whether it has participated in the execution where B3 was 1 and B4 was 1, if P2 is corrupt and try to do the analysis of the communication. Now, let us retain the same execution and try to argue whether this is the case even for a potentially corrupt P3, right. So, if P3 is corrupt, then view 3 consists of the following. View 3 consists of the information that the input of the party is 1, the overall sum is 2, the ciphertext C2 that it has received is 0, and the ciphertext C3 which it has communicated, that is 1. That is the overall view of the third party. Now, definitely based on this input 1 and the overall sum being 2, there are the following possibilities. It could be the case that B1 equal to 1, B2 0, B3 equal to 1 because that is fixed, and B4 equal to 0 because this configuration can also result in the sum being 2, or it could be the case that B1 equal to 0, B2 equal to 1, B3 anyhow is 1 and B4 equal to 0, or it could be the case that B1 is 0, B2 is 0, B3 is anyhow 1 and B4 is equal to 1, because this input configuration can also lead to the sum being 2. We have to show that from the viewpoint of this corrupt P3, these set of this view, this candidate view 3 could occur even for this configuration as well as this configuration as well as this input configuration, and hence it cannot pinpoint that the ciphertext C2 equal to 0 that it has seen is whether for the first configuration or whether for the second configuration or whether for the third configuration, and hence it could be any of these 3 possibilities, and hence it does not learn anything about the actual inputs of the remaining parties. That is what we will show here. Okay. So, these are the again same thing what we have done with respect to the corrupt P2. The question marks here denotes what are the things which are right now unknown from the viewpoint of this corrupt P3. The things which are not in question mark means anyhow that is part of the view of the corrupt P3. And now again P3 is making this analysis, mental analysis. He is now asking himself the question that she is asking herself to the question, have I participated in an execution where the input of the first party was 1, my input is anyhow 1, I have received the ciphertext 0 from my neighbor and I have communicated ciphertext, I have received ciphertext 0 from my neighbor and I have added my input and passed on the ciphertext 1 to my next neighbor. She is asking herself this question, and that is quite possible, because it could be the case that the one time pad which P1 started with was 4, which would have resulted in OTP encryption of 0 being forwarded to the second party would have added 0 as its input to the ciphertext and would have forwarded the ciphertext 0 to the third party. That is quite possible. Now, the corrupt P3 is asking in her mind, is it possible that actually the messages that I have received in the protocol corresponds to the case when the second party's input was 1, my input is anyhow 1, second party would have forwarded the ciphertext 0 to me and I would have forwarded the ciphertext 1 to my neighbor. Again that is quite possible if the one time pad picked by the first party would have been 4, and one time pad taking the value 4 can occur with probability 1 over 5, because the one time pad is picked uniformly at random. That means, this first box here could be a possible execution scenario from the viewpoint of the corrupt P3 with probability 1 over 5. This second box also could be one of the possible execution scenario from the viewpoint of the corrupt P3 with probability 1 by 5 if the pad would have been 4, and it is also quite possible that the one time pad picked by the first party was 0 and its input was 0, and then everything is consistent with view of what third party has seen. But what is the probability that the one time pad picked by the first party was 0? Again it is 1 by 5. So, that means with what we have shown here is that for the fixed B3 equal to 1, that is the input of the third party. Now, with respect to B3 equal to 1 and the sum being 2, for every candidate B1, B2, B3, B4, which along with this value of B3 takes the sum to be 2, this view 3 can occur with equal probability, and hence P3 cannot make out whether it has participated in this execution or this execution or this execution. Same analysis we can do even for a potentially corrupt P4 as well. Okay. So, view 4 will be now its input being 0, final sum being 2, it has received the ciphertext C3 equal to 1, it has received it has communicated the ciphertext C4 equal to 1. Again the question marks here the unknown things, and now let us try to analyze what could be the, let us see whether all potential B1, B2, B3, B4 with B4 equal to 0 and overall sum being 2 could be equiprobable from the viewpoint of this candidate view 4. Okay. So, this is one possibility that P2 and P3 has participated with input 1, that is one possibility here, and that indeed is possible if the pad which was picked by P1 was 4. So, this execution can occur with probability 1 over 5, or P4 is now analyzing whether it is the case that the first party and the third party has participated with input 1 and remaining parties have participated with input 0. Again that is quite possible if the pad would have been 4. So, this execution is also quite possible with probability 1 over 5, or P4 is asking in his mind that is it the case that the second party and the first party have participated with input 1 and overall sum turns out to be 2 and the remaining parties inputs are 0. Well, again that is quite possible if the pad would have been 4, and the probability that pad would have been 4 is 1 over 5. So, again what we have shown here is that if you take this candidate view 4, it is consistent with every possible B1, B2, B3, B4 with B4 being 0, because that is actually the fixed input of this corrupt fourth party, and the summation of this B1, B2, B3, B4 being 2, because that is the actual sum learnt in the protocol. Now, what about a corrupt P1? So, we have analyzed that with respect to 2 only the view 2 is independent, or with respect to view 3 only the view 3 is independent of the inputs of the parties, or with respect to view 4 that is independent of the input of the parties. Now, what about view 1? You might be wondering that view 1 has something additional, because the final key which is used for decryption that is available with P1. So, now let us try to analyze view 1 itself. So, view 1 will consist of B1 equal to 1, sum being 2, okay, and key being 4, and ciphertext 1 being 0 and ciphertext 4 being 1, right. So, with respect to B1 equal to 1 and S equal to 2, the other possibilities are that only B2 is 1, remaining other inputs are 0, or B3 equal to 1 and remaining inputs are 0, or B4 equal to 1 and remaining 2 inputs are 0. We have to show that each of these possibilities is consistent with this view with equal probability, right. So, let us first consider the case, can it be the case that B2 was 1 along with B1 being 1 and k was 4. So, k will be now fixed across all possibilities that P 1 is now thinking in his mind, because that is actually the value of key which it has used, and that is part of its view. Okay. And you can see that it is quite possible that the second party's input was 1, and that is consistent with whatever ciphertext P 1 would have sent to P 2 and whatever ciphertext it would have received from P 4. Okay. Also, it is quite possible that the third input was 1, that is again consistent with P 1's view, or it could be the case that fourth input was 1, that is also consistent with P 1's view. So, again this shows that view 1 is consistent with every candidate B 1, B 2, B 3, B 4, where B 1 is equal to 1, because that is actually the input of the first party, and the summation of B 1, B 2, B 3, B 4 is 2. Okay. That means P 1 cannot pinpoint whether it is this execution or this execution or this execution, right. So, now let us try to analyze that why this magic is happening. Is it just for the example that we had taken, or we can argue that if we take this general toy MPC protocol for computing the sum function, indeed the privacy property is satisfied. So, now I have written down the views of each party. So, in the view I have basically retained the messages which are received by every party, right. I have not retained the messages which it is communicating to the other parties, because the messages that each party is receiving, based on that and its own input, it can easily find out what is the message it is going to communicate to the neighbor, because that is how the message which each party is communicating to its neighbor is communicated. So, that I am not explicitly writing down in the rectangular box. I am focusing only on the inputs and the ciphertext that every party has received. So, to understand that why this magic is working, we have to basically see on what exactly is the ciphertext every party is receiving. So, if I consider a corrupt P 2, what exactly it is receiving? It is receiving an OTP encryption of the bit P 1, and that OTP encryption is indeed going to be a random value that will be completely independent of whatever B 1 P 2 makes as an hypothesis in her mind. That means, if P 2 thinks that okay, B 1 is, can B 2 be this, B 1 be this value, yes, that is quite possible, because corresponding to that there is a random key k which P 1 could have taken, and the OTP encryption of that candidate B 1 and that candidate k would have produced this ciphertext C 1. That means, based on this ciphertext C 1, P 2 cannot infer out whether he is seeing B 1 or B 1 prime or B 1 double prime or so on, because the corresponding k is not known to him. And this is the case even for P 3 as well, or for P 4 as well. Okay. So, let me make it more clear. So, okay. So, if I consider a corrupt P 1 here, okay. So, what are the messages a P 1 receives here? So, this is anyhow his view, it has its own random OTP key here, and this is the ciphertext C 4 that it has received and the ciphertext C 1 which it has communicated. I have to argue here that C 4 and C 1 anyhow C 1, he will be knowing what is C 1, because he himself has communicated C 1. We have to argue that C 4 does not help him to learn anything additional about B 2, B 3, B 4, because the k is known here, B 1 is known here. Okay. It is only the value of B 2, B 3 and B 4 which are not yet known to the corrupt P 1, if it is trying to infer anything about the inputs of the other parties, right. That means, this portion is not known to him. The sum as a whole is known, but what are the individual things he does not know here, right. It could be any question mark here, and indeed it could be the case that whatever candidate value P 1 makes regarding B 2, right. It is quite possible that he has forwarded a corresponding C2 and with respect to that candidate B3 that was added further to the received candidate C2 and forwarded to B4 and so on, right. So, the point here is that even though C4 is learnt by P1, okay, it is basically the summation of k and B1 and every candidate B2 B and a summation of every remaining candidate B2 B3 B4 which can sum up to S, right. So, that is why just by analyzing C4 P1 cannot tell whether it is the case that B2 is 0, B3 equal to 1, B4 equal to 1 or is it the case that B2 equal to 1, B3 equal to 0 or B4 equal to 1 or so on. It could be any candidate B2, B3, B4. Okay. In the same way, if I consider a corrupt P2, what is the message that it is receiving in the protocol? Anyhow, sum is learnt by him, sum is learnt by her. So, that is not a privacy breach here, but she is learning something about the input of the other party, first party, namely an OTP encryption, but it could be any input encrypted with any key which would have resulted in this sum C1. Okay. So, that is why from the viewpoint of P2 it cannot make out whether it is say B1 equal to a value x or whether B1 is equal to a value y, because corresponding to this x there is some candidate K1 which would have resulted in the ciphertext C1 which it has seen, or corresponding to this y there is a corresponding OTP pad K2 which would have summed up and produced a ciphertext C1. So, just based on the value of C1 that it has received, it cannot make out what is actually this B1, and that ensures that the view 2 is independent of the input B1, right. In the same way, if I consider a corrupt P3, okay, a corrupt P3 receives this ciphertext. Now, it does not know the following: what is B1, what is B2 and what is K. Now, for every candidate B1, B2 that P3 makes in her mind which is consistent with S, there is a corresponding K such that corresponding K along with the candidate B1 and B2 would have produced the actual C2 which P3 has received during the protocol execution, and that is why view 3 is independent of every potential B1 B2 pair, and I can run the same argument even for P4 as well. And that is why in this whole protocol, if a single party is corrupt and try to analyze the ciphertext that it is receiving from its predecessor, it cannot make out anything about the actual value of the inputs of the other parties. The actual inputs of the other parties could be any candidate inputs consistent with the view of the corrupt party and the overall sum, okay. And that ensures that this simple toy MPC protocol indeed helps the parties to compute the sum function in a secure way, right, which actually looked like an impossible task when we started with the problem description, but we showed here that even by exchanging messages among themselves, the parties can securely compute the sum function without revealing anything additional about the respective inputs. Thank you.